server. Yeah, got it.
Brilliant. Thanks, everyone, and thanks, Carl-Henrik and Challenger for doing all the hard work of pulling the program together, as well as Jess for what I thought was a really excellent kickoff to the meeting. So in some sense, I guess I'll carry on in the same vein, but very happy. I've got the chat up so I can see your questions and any comments Carl wants to put in, like I did for Jess's talk, or Jess wants to put in, or Challenger wants to put it in the chat. So this is sort of an introduction to machine intelligence. I'm also going to start from an odd place, something that I never thought in my career I would end up sort of thinking about and worrying about, but this notion of superintelligence. So Superintelligence is this book by Nick Bostrom from a few years back, I think 2014 or something, which got everyone excited about the possibilities of AI. And what I found interesting about it is how much of the sort of common conversation about superintelligence is embedded in this quote. So this is by Pierre-Simon Laplace, who, for those of you who don't know him, I mean, he's one of my favorite historical scientists. I mean, he lived into his sort of 80s, but was a sort of one of the leaders of the Newtonian world of post the initial sort of, oh, look, we can use maths to predict nature. I think he probably perhaps did more than anyone to sort of put that into practice. But by 1814, he's towards the end of his, or towards his later years, and he writes this philosophical essay on probabilities. And I often think when I look at it, is it an attempt to be seen more as a philosopher than a scientist? But philosophers don't seem to see him that way, but I kind of do. So it's got this quote in it, which you can read, but you know, just sort of highlights, given for one instance an intelligence that would comprehend all the forces by which nature is animated and the respective situation of the beings who compose it. An intelligence sufficiently vast enough to submit these data to analysis. It would embrace in the same formula, sorry, there's an error there, formula, the movements of the greatest bodies of the universe and those of the lightest atoms. For it, nothing would be uncertain. We talked about uncertainty a moment, and the future and the past would be present in its eyes. So this is obviously an English translation of a quote that was originally in French. And I just want to decompose it for a bit. So an intelligence, so already I always think this is such a funny loaded word. When you hear the word intelligence, I always think split it into two things: an intelligence as in an entity that's intelligence, or intelligence as a property of something. And normally I'm talking about it as a property, but here he's talking about it as an entity, which could comprehend by all the forces by which nature is animated. Okay, so I would say that that's a sort of our understanding of the universe, our sort of model of the way the universe works, and the respective situations of the beings that compose it. Now, in French, and certainly the French that I read, Laplace talks about data. In French, it's called données, les données. And of course, the etymology of the word data is from Latin, and it has the same etymology as données, as in that which is given to us. So sometimes it wouldn't be cool in English if instead of talking about data, we talked about givens. Oh, those are your givens. So when he's saying the respective situations of the beings that compose it, I interpret that as, in a modern sense, data. And the first part is the model of the universe. And then an intelligence sufficiently vast to submit these data to analysis. Well, one thing that Laplace and Gauss and all their contemporaries had to do was an immense amount of work on the maths to try and get these models to combine with data. They didn't have computers. So when he's saying an intelligence sufficiently vast to submit these data to analysis, he's thinking of the sometimes months it would take him or his contemporaries to combine their models with the data they've observed to make what comes next, which is the predictions. It would embrace in the same formula the movements of the greatest bodies of the universe and those of the lightest atom. And there would be no uncertainty. There would be no uncertainty. Everything would be as it is seen now. And this is a sort of famous quote. Can anyone put in the chat what this quote is known as? See how aware what it's called. Come on, I'll give you a few minutes. It's so famous. Laplace's Demon. Thanks, Blas. Perfect. It's known as Laplace's demon or Laplace's Superman or Laplace's determinism, but I kind of like the word demon because it's the notion is that there's this intelligence is a demon that can do these amazing things. And it's amazing because like in philosophy, this is spoken about and people refer to it. And no one ever looks at the irony of it and says, well, isn't it funny that he should say that in a philosophical essay on probabilities? And notice I've put which page it's on, page 3. So one of the things about this quote, which is not widely understood, but if you go and read the source, you see is this is Laplace's demon, but it's a straw demon. He's setting it's a setup. But it does describe the world as we have it today. Data plus model via compute going to prediction. Jess said I'd use this slide again. It's my favorite slide. The equivalent of Prometheus, clay plus Athena breath goes to human. Data plus model through compute goes to predictions. Now, intelligence isn't just about predictions because it's about acting on those predictions. And, you know, what action you choose to take is kind of dependent on what your objective is. And so one could extend this formula to try and include decision making, and then one would have to think about that a great deal. But machine learning itself is typically focused on this bit. I mean, if you go into reinforcement learning, you do take into actions and decisions as well. But a lot of machine learning is just focused on prediction. And that's where it differs from statistics, because in statistics, you tend to choose your model in such a way that it's interpretable. So you've got two things you can do here. In statistics, you tend to sort of build a data and experimental setup where you're going to get a deeper understanding of the mechanisms that are driving things. So often you're seeing linear models, and we already talked about randomization, and you're less concerned about the prediction. You're more concerned about your ability to act on what your model is telling you and make a decision that alleviates the pandemic or alleviates poverty or something like that. So you're perhaps less concerned about the prediction. Machine learning, you focus less on the interpretability of the model and more on the prediction. And you'll see that very much in the sort of models that are being used. And those models have risen to prominence because the predictions of those models are very good. So this is a quote from someone a bit closer to home, Stephen Hawking, from the book A Brief History of Time. This notion in physics of if we discover of everything, a theory of everything, it would be the ultimate triumph of human reason, for then we would truly know the mind of God. This is the thing cosmologists like to write, isn't it? I guess, you wonder, like, did he write it a bit on a whim? And then, of course, it's the most quoted bit from the book. But what I like about this quote is it's reflecting this notion that's also there in Laplace's quote, that look, in Laplace's demon, if you know everything, then nothing is uncertain. And then here Hawking is saying that you would know the mind of God. And what I like about it even more is we can see how that plays out, because what I'm showing you here is a creation, an environment where there is a theory of everything that we do understand. And the God looking very godly on the right there, I guess small g God, is John Conway, the mathematician. And what we're seeing on the left is two images of sets of pixels. So the pixels in these images, the background is moving, so the pixels are effectively moving, but we're tracking the pixels in these cases, are obeying very simple rules. So each pixel is sensitive to its neighbors. So you have a grid of 9 pixels, and the pixel in the center is responding to the number of neighbors it has. If there are 3 neighbors, then a new pixel is generated in the center. If there are more than, actually, I can't remember exactly all the rules, but the set of rules are that the pixel either lives or dies according to its neighborhood, right? And it's very, very simple. And we understand these rules completely. And as a result, from these rules, you get these patterns forming. And these patterns are things that are sustained by these rules. This one here on the left, so Conway developed this in sort of 1970, that sort of era. And almost immediately, this pattern was discovered. It's known as the glider. And the glider is a pattern that moves across the background when it follows these rules. So this is known as a cellular automata. Oh, there we go. There's that's the kind of challenge to put the rules in. Any live cell with 2 or 3 live neighbors survives. Any dead cell with 3 live neighbors becomes a live cell. So that was the one I remembered and then stumbled. So if a cell is blank, like this one, if it has 3 neighbors in the cells around it, it appears in the next term. Right? If a cell is there and it has 2 or 3 neighbors, it survives to the next round. For any other number of neighbors, the cell either dies due to loneliness or dies due to overcrowding, so it disappears. Very, very simple rules. But the pattern on the right is called a loafer. And it's another of these glider things. It's actually moving across the left-hand side, so it's not moving diagonally. It wasn't discovered until 2013. And what's interesting about that is this game of life, it's a world where you've got this pixelated background, right? And you could simulate it on computers, or the first work they were doing, they would simulate it on pieces of paper. So you understand all the laws of this universe. You understand everything Laplace is talking about. But this pattern, which tends to move slowly to the left, it moves slower than the one on the left here, is only discovered 43 years after the game is invented. And that's showing us one of the problems with what Laplace is talking about. While we may know the fundamental laws, to play those laws out, to see what the world is around us, requires an enormous amount of compute. So it's not sufficient to know the theory of everything. So that's one of the parts of what Laplace is saying. Even if you did know the theory of everything, you still have to do computation for 43 years over lots and lots of people looking at this thing before you find a pattern like this. Now, it reminds me, you might think, well, okay, what's that got to do with science in general? But it reminds me of a challenge that you get in climate simulations. So climate simulations are similar in that you take fundamental rules encoded in Navier-Stokes equations, and say in the UK Met Office, you put those rules into a simulation. And that simulation itself just plays those rules forward. That simulation does not know about hurricanes. That simulation does not know about tornadoes. That simulation does not know about all the environmental effects and the way the oceans move. It's a very low level thing. This is the equivalent of a hurricane. It's something that is emergent from those simple rules. But in order to detect it in the simulation, you actually have to write code. And that's what one of the things, colleagues at the informatics lab have done is you have to write codes that define what hurricanes look like so you can detect the hurricane operating in your simulation. Of course, we live in a world where we observe the simulation. Yeah, so nice question from Alex. What about the inverse, from observing the gliding patterns to infer the rules? What demon does that take? Well, that's our job, isn't it? So Alex is saying, well, if I observe these things, how do I infer the underlying rules? That's science, isn't it? That is science. Of course, here, the underlying rules are simple enough that, I mean, it might take you a while, but eventually you would be able to show that all that happens is local, right? And the global effects that we're seeing are all a result of those local patterns. So what we're seeing in terms of, we do see global things happening. You can build Turing machines in the game of life. So you can build universal computers, right? But all of that here is down to some set of local rules. But that's the game of science, isn't it? Is to look at those high-level patterns, to look at the hurricane and say, oh, what causes that? Oh, it's conservation of momentum. It's not your immediate thought, is it? In a compressible fluid. Okay, so that's the challenge we face, reversing that. But even running it forward's hard, is my point here. So reversing it is known to be hard, Alex, but running it forward it's actually very hard. But as I said, Laplace was not dumb. He was the opposite of dumb. And I think it's embarrassing the extent to which we quote him as the source of this notion of Laplace's determinism. And we think how unsimplistic that was, because the entire essay is about the opposite. So he goes on 2 pages later in a less pithy quote to say, well, look, the curve described by air or vapor is regulated as surely as the planets are. But there's a big difference in that there's ignorance. We do not understand. We are ignorant about what is going on there, right? And then he says probability is the way of modeling that ignorance, right? So this is incredibly important to me. And this goes along with what I was saying before. And I'm going to sort of riff on this theme for a bit and tell you a bit of historical context for people who have looked at this. That I think we often look at things the wrong way around. We tend to, and it affects the way we model things. We tend to focus on the fact that we're modeling what we know. We are trying to do that, but actually a lot of what our modeling is about is correctly modeling what we don't know. And that is where uncertainty comes in. That's where probability comes in. And so in an effort to try and get people to realize that this is an important concept, and this is what Laplace was talking about, I've christened this Laplace's gremlin. I don't know. So yeah, who knows where do gremlins come from? And yes, there was a film about them, but where do they come from before the film? How old are they? Do they go back? Were they there with Prometheus, or are they more recent? Actually, interesting audience. Who's even seen the film Gremlins? But actually, they predate the film Gremlins. Anyone know? Good heavens, you're learning so much today. Okay, so Gremlins was a film about mischievous creatures, but the original mischievous creatures came from, I think, the RAF flying missions during the Second World War. And they would, obviously things would go wrong with planes. They would fall out of the sky. They weren't as reliable as you'd hope. You know, imagine making those planes in a rush. And there became this sort of folklore notion. And people even said that they observed them, that they saw a gremlin interfering with the plane engine. There's like records of, I looked out across the wing and I could see a gremlin pulling on my fuel line. So there's actually quotes of people saying that. This notion of a small creature, homunculus, that interferes with your plans and disturbs them actively. And so I kind of really think it's an appropriate creature, because it only dates back to the sort of late 1930s or early 1940s. But I think it's such an appropriate creature to think about in terms of what affects our modeling, that the gremlins are there. The gremlins of modeling are there damaging what we do. And now you have to watch the film Gremlins as well. You got Lockdown. Yeah, we all look from Jess. Pilots who carry mascots of Lucky Gremlins too. It's really sort of there's a lot of interesting psychology behind that. Imagine you're doing such a dangerous thing. You would prefer to think a mystical animal is on the wing of your plane than, oh, well, that's just bad luck. So this shows like how anti-thinking about probability we are. So I kind of like telling stories, and the story of like what the theory behind these things actually also has some parts in Cambridge. So the gentleman on the right here is Norbert Wiener. The gentleman on the left you probably recognize as Bertrand Russell, and in the middle Albert Einstein. And why I mention these three people is because there's this sort of really interesting, the sort of 20 years before the Gremlins came on the scene, there's this really interesting meeting of Wiener on the right and Russell. Russell was working on logic and trying to develop theories of maths and everything that based on logic. And Wiener was about 19 years old. He was a child prodigy, and he was visiting after he'd finished his PhD at Harvard in an effort to become a philosopher, studying under Russell. But they really did not get along. And but I mean, Russell wrote letters about how annoying he found this precocious American, and Wiener wrote letters about how annoying he found Russell. But Russell was good enough to still work with Wiener and sort of guide him, and sort of realize that actually his interest was more in maths. And he showed Wiener a paper from 1905 by Albert Einstein, which was a paper that was explaining Brownian motion. And Albert Einstein, in that paper, sort of came up with a mechanism that describes Brownian motion that basically says what you're seeing is the result of atoms piling into the particles in the pollen. It is not pollen itself. Particles viewed in a pollen. Brown was a botanist, but he was looking at pollen. He was trying to understand sexual reproduction in plants, and he was looking in voids in the pollen, and he saw these particles that were moving, very, very small particles, much smaller than pollen. And Albert Einstein came up with a mathematical model for that. And that was an approach that then Wiener really took on. He said that model, which we'll talk about more in a moment, was kind of the inspiration for what he saw as a theory of ignorance, a theory of uncertainty, which we will see is exactly what Laplace said it should be, based on probability. So those theories themselves go to, unfortunately, I mean, all these scientists from particular eras, as you can sort of see. So every time you group of scientists, they all look the same. And so this is the era of the beards. We've got Maxwell on the left, Boltzmann in the middle, and Gibbs on the right. These are the sort of three fathers of statistical mechanics. And Maxwell in particular took this notion from Laplace, not directly from Laplace, he actually took it from statistics and started saying what happens if you apply uncertainty to mechanics and try and use that for explaining heat. So Maxwell's was the first work that sort of said, well, there's a lot of, what if the theory of heat is the movement of the unknown? Boltzmann did an enormous amount of work building on that, and then Gibbs also did an amount of work on that. But what I like to do is just sort of show this sort of happening in practice. So this is my notion. I've got some little bugs in my code which I need to fix, but so the balls move a little bit when they touch each other, and that will soon sort it out. But what I'm showing here is some billiard balls sort of initially moving up and down in straight lines. And the measure that these people who were effectively working in a field called thermodynamics, which views the particles in a fluid as sort of molecules interacting with each other or not interacting with each other unless they collide, is Boltzmann's model of a fluid, is an ideal gas model, as a sort of bunch of billiard balls bumping into each other. And the reason I started them out moving in a direct line, sort of up and down, is because I wanted to highlight that that moment, you sort of know, very strongly something about the energy in this system, because the state of every one of these molecules is aligned in terms of their momentum is the same, their velocity is the same, and they're just bouncing up and down. But I initialized them with very small differences in their initial conditions. So there was some unknown about their initial conditions. And the system of billiards is what's known as a chaotic system. So that, these come up a lot in science. And the chaotic system is one where the sort of conditions in the future are very sensitive to initial conditions. And what you actually tend to get with this, although everything in this is deterministic, this is entirely deterministic code, what we see is that the balls are moving at any one moment. We can actually try and histogram them, and we see a distribution. So because I started at an initial velocity, there's a peak in the distribution, but you can see this histogram here. This is the distribution of velocities. And what Maxwell proved is that this is Gaussian, right? So if I skip 1,000 seconds in the simulation, even that peak will start to disappear. Now, what they did in that system is they measured. Before them was already a notion of something called entropy. So entropy being, as we would understand it in machine learning, the sort of amount of ignorance in the system. So the notion of entropy in thermodynamics turns out to be, and people on the call will know this better than me, but it's the amount of energy that is locked away in the microstates of a system. So in this case, the microstates are the positions of these particles that you can't access if you only have access to things like the pressure and the volume and the temperature, macrostates of the system. But there's a strong duality between this and artificial intelligence, because this is representing sort of, it's saying we use probability to sort of represent the unknowns, and entropy turns out to have a probabilistic interpretation, an information theoretic interpretation. And that's what Wiener converted it into. So the entropy of this system I'm measuring here is 2.68, right? So this is measuring the entropy of this distribution Gaussian here. And you can see over time it's going up. We have these laws of maximum entropy that says we expect entropy to increase. So the entropy at the start was low when everything was moving in the same direction, and it's increased over time. Now, we'll not read this quote, but Maxwell wrote about this in The Theory of Heat. She's 1871, which was, I mean, a sort of remarkable book. I think today we know Maxwell more for Maxwell's equations, which are theories of light. But in his time, he was better known for his theory of heat. And you can imagine why, because he was giving explanations for the macroscopic properties of steam engines, which was obviously very important. In fact, I think there's a wonderful duality between information engines, what we're trying to work with today, around processing of data and converting data from one form to another, and steam engines, which are processing energy from one form to another and turning it into useful work. But in our world, like, useful work is energy in a form, or it's the state variables in a form that we need to take actions, right? Which is actually very similar to work in physics, right? It's energy in a form that we need to take actions. But in our world, it's sort of, we're trying to convert these systems into things where we can draw conclusions or inferences. Now, this is describing the next bit, which I'm going to just actually show by diagram. So we had Laplace's demon. Well, Maxwell is also famous for a demon as well. And Maxwell's demon was about that system we just looked at, which has the same bug in my JavaScript code. So the balls will move around. Now, Maxwell looked at the system that we'd seen before, and he said, well, what happens if there's a demon? And Maxwell's demon does a different thing to Laplace's demon. Maxwell's demon has the capability to observe the speed of the particles in the fluid. And Maxwell's demon, what it does is says, look, if the particle is moving fast, I want to keep it on the right-hand side. If the particle is moving slowly, I want to keep it on the left-hand side. So what I'm doing here is I've colored particles that are over a certain speed, red for hot, and particles that are under that speed as blue. And then I've put a barrier that this is what the demon controls. The demon allows, it's porous. On the right-hand side, it's porous to red. So it's porous to blue, sorry. It's porous to anything that goes from right to left that's blue. And on the left, it's porous to anything that goes from left to right that's red. So if you track the red balls on the right, they bounce off the barrier. But if you track the blue balls on the right, they go through, right? And that's what Maxwell's demon is given the ability to do. Without use of energy, there's all this sort of constraints on how the demon behaves. Without use of energy, the demon is capable of observing the system, making a judgment about whether a ball is going above or below a certain speed, and deciding which chamber to let it into. And what the demon is therefore doing is ensuring that the right-hand side is hotter than the left. And this was a sort of really interesting, Maxwell introduces it in that quote on the previous page in his theory of heat, to try and explain to people that the second law of thermodynamics is a statistical thing. Sorry, look, I've got a bit stuck there. That doesn't happen in real molecules, that happens in my code. So Maxwell's trying to use it to sort of explain to people that the second law of thermodynamics is a statistical theory. It's not something that holds when you get down to the small microscopic world and start playing with the microscopic states, the microstates. But actually, it became a real inspiration for people to think about this trade-off between information and thermodynamics. So people tend to associate information with Shannon, who's the late 1940s. Oh, yes, thank you. Sorry, I had got, Alex has asked if this is a histogram. So let me histogram it. Yeah, I've been trying to do the maths, Alex, on this for you. The form of the histogram, I believe, and the maths, I'm not like, I haven't yet gone to Challenger, who would really be able to genuinely help me with this. But I've applied maximum entropy approaches. And the form of the histogram is interesting, like, because it's truncating, what you get is like, you can see that on the right, you do have some slow particles because it takes some time before that they move to the left. And you can see on the left, you have some fast particles. But what I think you get, and I think you can sort of see it in the joint histogram here, is you get a mixture of two distributions where the middle of the slow velocities from the middle are cut out and reduced on the left-hand side, and they're reduced on the right-hand side, and they're increased on the left, right? So why I wanted to compute this is because I wanted to be able to compute the entropy and compute it analytically. Here I'm computing it numerically, because the bit I'm sort of getting to now is that there's this sort of mystery about where this decrease in entropies come. Right, so here the entropy is 2.68, and here with the demon interfering, the entropy is 2.63. And if we skip forward, it will go up a bit, but it stays that little amount down. So it's like there's a reduction in entropy relative to the first, right? And that entropy loss turns out to be the information that the demon has, right? So the demon is interfering with this system by making observations, and they have access to information themselves. And there's an enormous amount of fascinating work around the theory of computation, going back to 1929, a guy called Szilard, who actually reduces this system to a one molecule system and starts analyzing it, and sort of says, well, in that case, the knowledge of the demon is whether it's on the left-hand side or the right-hand side for one molecule only. And then he makes a direct equivalence between what we think about as entropy and what we talk about in the information era as information theory. And that's 1929. Wiener is very involved in this area as well, as part of communication theory that's merging across the time, across analog lines, you know, for sending telegraph signals, telephone signals, this sort of thing. Okay, thanks for the question. I don't forget to do my histogram, Alex. So what's going on there is that the demon is measuring the system and gaining information, and is putting that to good use. There's actually a load of work around whether measurement requires energy and all this sort of stuff. And so a really nice read on this is, if you want to see a summary of this work and you're interested scientifically, is Feynman's lectures on computation. They're edited by Tony Hay, who actually is also working on AI and science. He's a physicist that did a postdoc with Feynman, but he's leading AI and science for the, I never remember the name of that research council, the structural, Jess will put it in the chat, STFC. Look, I said that just as she puts it in the chat. The STFC, the research council that deals with facilities, Tony Hay, he edited these lectures that Feynman gave on computation that talk a lot about the thermodynamics of computation. Really fascinating area. But I'm just trying to bring it up to give you this sense of the history and the scientific basis of uncertainty. Okay. So what's that got to do to us? Well, I want to sort of point out something that I find very, very important, and I bring it in too slowly. So I'm just going to bring it all up at once, right? So there's something remarkable about our intelligence. And what I want you to sort of see here is, on the left, a computer's ability to communicate and compute. And in the middle, our ability to communicate and compute. And on the right, there's a gentleman named Jean-Dominique Bauby, who was the French editor of Elle magazine. And he wrote a book, and he wrote a book after his brainstem had been knocked out by a stroke. So his ability to communicate and compute was severely reduced, severely reduced. And that's a syndrome we would describe as locked-in syndrome, right? So what you see here is someone responding to him winking to take down what his thoughts are. But the point I want to make is, if you look at our ability to communicate in terms of the demon, the amount of entropy we can reduce over time, entropy can be measured in bits, right? So if we ignore Boltzmann's constant, we can just measure directly entropy in bits, and we can communicate about 2,000 bits of information a minute. That would be equivalent to Laplace's demon communicating, in that one molecule case, the location of the molecule either being on the right or the left-hand side of a divider, doing that 2,000 times in a minute. Now, that's me talking. Writing would be slower. But what's interesting about us, if we look at our ability to process information, our ability to sort of take that information in our brain, and the problem is in our heads, we can't measure information so easily. But if we look at how much computational effort it would take to simulate a brain, what we find is that we're making a billion calculations per second, right? So our ability to process information is massive compared to our ability to communicate. And so this leads me to think about and talk about a lot something that I think of as the embodiment factor, which is, imagine I wanted to communicate 1 second's worth of neuron firings from my brain, and I wanted to share that with you by telling you. So if I had access to it, which of course I don't. So I'm not just talking about the sort of thoughts I'm aware of, I'm talking about everything that's going on in my brain. If I started telling you those neuron firings at the rate I can communicate, it would take me 5 billion years to communicate 1 second's worth of neuron firings, which is quite a long time. I mean, it's like longer than the Earth's been around, and order of magnitude as long as the universe is. What's the universe been around, like 7 billion years? Now, if you compare that to a computer, the computer can communicate with billions of bits per minute, as it's doing now between our different computers to communicate this video. And modern computers, like on our desk, do about 100 billion calculations per second. The fast computer can get up to this, like the fastest computers we have, HPC, 14 billion years. Oh, so I got it hard. Out by a factor of 2. That's fine for physicists, right? So I could tell you it 3 times during the length of the universe. That was 3 seconds worth of firings in my brain. Embodiment for the computer is 20 minutes. So like for a computer to communicate 1 second's worth of firing, yeah, the theoretical physics factors of 2 are right. Yeah, that's right. Up to a factor of 2 or pi. So the computer would take 20 minutes to communicate those firings, right? Which is a lot less. And if you compare us to Jean-Dominique, who's been locked in, he can communicate at around 6 bits per minute. That's how fast he was going to write his book. If you sort of read it, I mean, it's a good book. It's called the Diving Bell and the Butterfly. It's written originally in French, but there's an English translation, and there was a film as well. I haven't seen the film. I've read the book. He's doing the same thing as us in terms of calculations, but he can communicate less. So yeah, 15 trillion years is how long it would take for him to use information theory to communicate everything, not use information theory, to communicate everything he's thought in that 1 second. But it's much closer to this than it is to this, right? We're in the same domain as Bobby. So human beings already, and this relates to a lot of the things that Jess was saying earlier about interdisciplinary communication, all the challenges of understanding this, because this has a sort of really particular effect that when 2 humans talk to each other, you have to go through this thing because you've got to select what to say. You've got so much compute. You've actually worth spending a large amount of time thinking, both consciously and subconsciously, and you're doing both, what the right thing to say is in order to communicate the idea. So you have a model of the person you're speaking to. You say something in order to communicate some idea in your head. And that person, when they hear that, they have a model of who you are, and they may even have a model of who they think you think they are. They'll combine that with what they've heard, and that will cause them to make a response, like a question, which you can ask, by the way. Maybe we'll stop in after the next slide to get questions in. Or maybe I'm so close to I'm not sure how close I am. So that's how communication is working. Then they respond with something else. But there's an immense amount of modeling. So this is why humans tend to anthropomorphize. And I don't like saying that word, so I'm inventing the word anthrox, where X stands for pomorphize. Anthrox each other. So we tend to sort of treat objects as if they're humans because we like to communicate with them. Now, of course, if this works, this is really beautiful because you can share ideas. And it's why it's so nice to work with people who think a little bit like you, because you think what each other's thinking before you say it. But if it doesn't work, it ends up with arguments, right? Because if you've got slight mismatches in the models or you say slightly the wrong thing, then you end up talking across each other, which happens a lot. Now, what I find very interesting, relatively speaking, in this context is we have this problem with computers. This is what I was referring to earlier when we're trying to communicate the conclusions in a computer to a scientific expert. that the scientist has some understanding of what a computer says. So tries to give it some input, tries another input, computer says that, computer says no, and you end up with a sort of argument. And this is immensely problematic when it comes to dealing with these artificial systems in any domain, science included, regardless of the domain, because we don't communicate, or we don't have the same intelligence as the machine. So getting an understanding of the why this machine is making these conclusions, a general understanding, an ability to model it in your head becomes absolutely critical for you as a scientist. This is very much the same thing as, you know, like, well, I understand how a car is going to respond to me as I drive it in that analogy we gave earlier. I don't necessarily need to know the technical details, but I need to know something at a broad level. Okay, I'm going to skip through that bit, and because I want to get to questions, and I've communicated most of what I wanted to say. So one way I tend to think about when I'm introducing these models, deep learning's done an enormous amount to advance this capability to make predictions in artificial intelligence. But really all that's going on is what I like to think of as a pinball machine. You're getting some input as an image, which is then going through a series of simple functions and being mapped to an output. So it's just a mathematical function with all these complex connections. And the reason it can do this is because it sees a lot of data, an enormous amount of data. And that's very, very different from us, because we don't see that much data. We can't see that much data because of the embodiment factor thing. So the way the machine is drawing conclusions, and Jess drew this out beautifully with her example, in the case of the Who Wrote the Wizard of Oz books, the data that the computer used was and the, not, you know, mortified, or I don't know, conglomerate, or these words that would stick out for us, because the computer can operate on these high frequency count things in a well-calibrated way. Whereas we're like magpies with our thinking. We tend to look out for sort of things that stick out and try and compute on that due to our low bandwidth. The beautiful thing is, like, well, what if we can bring those two things together and try and build a system where we've got both of those things going on? So I had a couple of examples in case I went slower, but I'm going to go straight to this sort of point around the program, because I'd rather you ask me questions. So the challenge we face, I think, when we're looking at accelerate science is represented by this diagram here. There's been a lot of work done in the domain of data-driven modeling, machine learning. I've built a neural network, it can detect faces. There's also been a lot of work done in what I refer to as mechanistic modeling. I've worked out how to implement the Navier-Stokes equations. As I said in the chat, the first implementation of numerical weather simulation was actually done on EDSAC-2, the second machine built in the computer lab. The grid sizes were enormous, so it was next to useless, but it was a demonstrator of numerical weather simulation. Before then, it was all done by interpolation and extrapolation of weather patterns. But that mechanistic understanding that goes into those simulations that we use today down at the Met Office, we've put a lot of work into that. Now, I see this challenge for Accelerate Science as being very much in the middle. As Jess also described, there's this sort of interesting thing. Well, now I can see the world in a slightly different way. I can see it through the computer's eyes. If I can model and understand the computer and how it's representing things, I can augment myself with the computer's understanding. But critically, the computer has to be able to communicate with us, or we have to be able to present the computer's conclusions in a way that our collaborators and experts can understand. So to me, that goes down to this cycle, which is omnipresent for you, that you're doing experiment, analyze, design at all times, right? And the design of your modeling, this is sort of where the machine learning is coming in. And you want to be doing this. You want to be turning this handle. You cannot afford to be constantly calling up someone in the computer lab saying, I need a new neural network, or I need PCA to be done. Can you do that? I used to call that at Amazon. I use this plot at Amazon a lot as well. I used to call that 1-800-SCIENCE. Hello, I need some sciencing done. For us, it was science because it was data science, and these were like supply chain questions. You don't want to do that. You need to have that capability yourself. And that means you have to have a good understanding of the analysis methods you need, the designing of the new models, and the experiments you want to do. And bear in mind, these experiments can be computational. They can be in silico, right? They can be simulations that you're running yourself to try and test your systems and inform what you're doing. And very often they will be in the physical sciences, right? So what is Accelerate Science? Well, we're trying to do this step change in science through machine learning, through bridging these worlds. And it's basically, fundamentally, it's you. And you are the program that we brought through the data science for science. And now we're trying to sort of bring through, turning into this community that will be the people that are out there that start having a good understanding of how and where to deploy these technologies. And then if you want, just as a sort of final thing, I've included a link to the course Carl-Henrik and I taught that really takes some of the philosophies I've just shown. So this was a new course we taught this last semester. Some of the things I've not talked about here are in this lecture on simulation here, if you want to go through and read the details. And really that was designed from scratch. We've not seen a course like that before, but it's totally targeted at trying to give you a scientist an understanding of the parts of machine learning, well, a significant part of machine learning they need to know to bridge the gap between the mechanistic and data-driven worlds. That's everything I think I wanted to say in this session. So I'm going to stop sharing so we can go to questions.
Fantastic. Thank you very much, Neil. It always feels a bit strange with Zoom presentation when you can't applaud, so I'll at least applaud Neil. That was very nice. So
I have such a large ego, I'm imagining cheers and applause. I'm assuming everyone's standing up, actually.
Yeah.
Some whooping going on.
It's all about this thing about having a model of your
yeah, you see, I've got the model of who you are in my head. Yeah, I am the orange person, or the blue. Was I blue? I can't remember which. You know, and in my head, you thought that was amazing.
It was.
In your head, you think I'm an idiot. There you go. That's the way it works.
Fantastic. So, do we have any questions? I'm going to stop the recording now. So, no one needs to be. You won't stop recording.